So we were saying that we'll do the Taylor expansion in order to find the expression of T east, T west, function of Tp. Okay? So first, if we start by the point at east, the distance between P and E is delta x east, which is equal to delta xp because we are considering a uniform grid. Okay? Now, from Taylor expansion, we know that we can write Te equals to Tp plus delta x east times the first derivative of T with respect to x at P plus delta x square over 2 times the second derivative of T with respect to x at P, and we'll stop here. If we do a truncation here, then the leading term, if you want, from the other side will be of order delta x to the power 3. So we say here that we will do a truncation, and then if we do this truncation, the error will be of order 3. Now, let us do the same for T west. Okay? So now if you do the computation of T west, then because west point is before P, then you will write minus delta x west here. So TW is TP minus delta x west dt over dxp. Here, whenever you have an even coefficient, minus بتروح. يعني plus delta x square over 2 times second derivative of t with respect to x at p, plus an error of order delta x3 because we did the truncation here. Okay? Now, what I want to find is what? The second derivative. To find the second derivative, if I look at my expressions here, I can say that if I add these two equations, the first derivative will cancel out. Why? Because I have plus delta x east dt by dx at p minus delta x west dt by dx at p. But since it's a uniform grid, these are equal, so they will cancel out. And then I can find an expression of my second derivative, because if I do the addition, I get T east plus T west equals to 2Tp plus هلا مثل ما قلنا انا وياكم فيكم دغري تحطوا instead of delta x east delta x square, okay, or instead of delta x west square over 2 delta x square over 2, يعني you have plus 2 times delta x square over 2. 2 and 2 will cancel out, okay, times second derivative of t with respect to x. And of course, the error will be of order. When you add two errors of order 3, you will have an error of order 3. So plus an error of order delta x cubed. Now, because your purpose is to find an expression of second derivative of t with respect to x, what you will do, you will take all terms to the other side and you will divide by delta x squared. So you'll get the following. You will get t east plus t west minus 2Tp over delta x squared is equal plus a certain error. هلا انتبهوا على شغله، الايرور هون is of order delta x cubed, but because you will divide by delta x square, so the error you will obtain will be of order of delta x equals to the second derivative of t with respect to x at p. So now what we did together is that we found an expression for the second derivative of t, function of t east, t west, and tp, with an error of the order of delta x. And this is a first order error relation.
غير سؤال.
Yes.
احنا ليه كتبنا 2x؟ ليش
نعم.
كتبنا 2x دلتا x سكوير ما تركنا هي زي كده؟
ليش كتبنا؟ ما كثير فهمت
ليش
عليك.
عملنا؟ لحظة بس جرب حط ايفون جوتي بحيث الصوت.
أنا بجاوبه دكتور، لأنه دلتا إكس إيست قد الدلتا إكس ويست ونحن عم نعمل سميشن بينهم.
بس شو سؤاله شربل؟ فيك تقول لي شو سؤاله؟ لأنه ما سمعته مزبوط.
عم يسأل ليه كتبنا 2 times دلتا إكس سكوير أوفر 2.
دلتا إكس سكوير أوفر 2 لأنه هيدي قصده هيدي؟
إيه وقت كتبتي وقت عملتي سميشن كتبتي 2 times دلتا إكس سكوير أوفر 2.
لأنه دلتا إكس إيست أوكي equals دلتا إكس ويست، لأنه هن قالوا لنا يونيفورم جريد، يعني دلتا إكس إيست equals دلتا إكس ويست equals to دلتا إكس. أوكي؟ فبما إنه أنت عامل أخذ الأسامبشن of uniform grid، then you can replace delta x east square over 2 by delta x over 2 delta x square over 2. وهون كمان مطرح delta x west square over 2 you can write delta x square over 2 because it's a uniform grid. هلا إذا منا uniform grid ما بتعود تزبط هيدي الإكسبريشن، تصير much more complex. Okay, so this is why إنه هيدي technique is good to use for uniform grids. وإلا إذا non uniform بيصير عندي هون هول two terms will not cancel out. Okay, يعني بيضل في ساعتها second derivative و first derivative. بس بما إنه it's a uniform grid these two terms will cancel out and these two coefficients will be equal. So when you do the addition بيطلع لك 2 times delta x square over 2 and 2 will cancel out. Okay, clear?
Okay, thank you.
Welcome. Okay, so now if we replace back if we do the truncation here, this is a first order error computation. I can replace in this equation k second derivative of t with respect to x by te minus 2tp plus tw over, as we have seen, over delta x square. Okay, so here if you do this replacement you will get a numerical equation instead of a differential equation. Okay, so doing the replacement you will get the following equation, and now you are able then to have a numerical equation and you can define your coefficients. يعني مش نحن كنا نكتب مثلا انه we write a east t east، اذا عم نشتغل 1D a east t east plus a p tp plus a west t west equal to a certain source term صح؟ equal to bp. Let us define the coefficients here. What is a east here? What is the coefficient of t east? K over delta x square. So k over delta x square. This is a east. Okay, and AP in general sorry, if you keep Q to this side and you take these terms to the other side, okay، يعني نحن عادة بنخلي السورس term يكون يعني نحن بنجرب نكتب الايكويشن يكون الكويفيشنت AP هلا هنشوف ليش بعدين يعني what is the cause. ناخد AP positive. Okay. So here to have AP positive, take the whole terms to the other side. If you take these terms to the other side وبتتركوا ال Q هون تطلع ال equation as follows. تطلع Q equals minus K TE over delta X square. يعني ساعتها ال coefficient AE هو minus K over delta X square plus 2K TP over delta X square. So the coefficient AP will be plus 2K over delta X square. This is AP. This is AE. And minus K over delta X square times T west. So this is the coefficient A west. Okay. So now we are back to the previous case. يعني حولنا differential equation to numerical equation, and these are the coefficients. Okay. So you can define now your coefficients. Okay. AP, AE, AW, and BP. And once you do this, you can solve in several methods. You can use, as we said, Gauss-Seidel, Jacobi, LU. You can use TDMA, etc. Okay. So don't worry, we'll practice on this. I will send you a series of problems to practice with, and we will correct them together. Now we will start with. It's the same idea, yani, if you want, but more, little bit more advanced. Instead of just taking diffusion, we'll take convection plus diffusion. Okay. So I will upload this for you on e-learning. Now we will start with a new chapter, which is the finite volume method for convection diffusion equations. You will see that it's the same methodology. So we have a differential equation. We want to develop techniques to solve it. One of the techniques is finite volume. The finite volume, as we mentioned before, consists on dividing the domain into control volumes. And for each control volume, we write the conservation equation. And after this, we define coefficients for the different variables, yani at the center of the cells and the neighbor cells. And then we solve these equations. And it's the same approach, but now we will take, instead of pure diffusion case, we will take the convection diffusion equation. So where you have both convection and diffusion. So always the first step to start with is to write the general equation. And then we start to simplify terms as we did together before. So if you take the most general equation, you have the transient term, the convective term, the diffusion term, and the source term. Now, when we consider the pure diffusion, transient and convective terms were both zero. Now, since we are considering both convection and diffusion, then we'll consider the transient term zero. And if we don't have a source term, in case they just say, no, we have convection diffusion without source terms, we can cancel out this term. So the equation will be, by just taking into consideration convective and diffusive fluxes, we'll just have this equation. So this is the convective flux. This is the diffusive flux. And summation of these fluxes is equal to zero. It's true that it seems that the diffusive flux is more complex than the convective one, because you have grad of grad, while here just have grad of rho v phi. So if you want in 1D, let us write this equation in 1D. In 1D, we said that grad operator, okay, is equal to del by del xi plus del by del yj, etc. But since we have 1D application here, it's del by del xi. And you are doing dot scalar product with rho times velocity vector times phi, okay? Since it's a 1D problem, so you have only velocity along x, so you can replace rho v phi by rho u phi along I. So when you do the scalar product, I dot I is 1, you get del rho u phi by del x. So, and here because it's 1D, we can replace del by d. So d rho u phi by dx minus, if we apply for the diffusion, as we did in the previous chapter, you get minus d over dx times the diffusivity coefficient times d phi by dx equals to 0. This term seems simpler than this one, but we'll see that it will add a lot of complications to the solution, and it can cause divergence. This is why we should do specific treatments to solve when we have convection and diffusion at the same time. So what is the idea? We'll see together that if you have pure diffusion, you have that the variation of the variable within the domain will be linear. Okay, so if you only have diffusion without source term, what will be the equation? The equation will be, if you go back to the equation here, okay, you just have that this term is 0. Okay, so if you just have diffusion without anything else, you have that d by dx of diffusivity times d phi by dx equals to 0. This means that tau times d phi by dx is a constant. And if you have constant diffusivity, if the diffusivity is not variable, then this means that the derivative of phi with respect to x is constant, and this means that phi will vary in a linear way. This is why we say that for case of just diffusion without source term, the variation of the variable will be linear. Okay, while for convection, no. For convection, if you in general, the convective flux is more affected by if you want the direction of the flow velocity. So if you have, let's say, a flow going from west to P, from west point to P point, the value of the temperature at P will be affected by the value at west, because it will transport it. The convection flux will transport the variable in this direction. So the convection is very dependent on the direction of flow. If you take a flow in the other direction, then the value at P will be affected by the value at east. This is why we say that for convection in general, we use an upwind scheme. And we consider that if we just have convection, then the value will be transported in the direction of the flow, and it will be like constant, because if you go to this equation back, if you just consider convection, okay, if you don't have this term, you have rho u phi equal to constant. Okay, because the derivative with respect to x of rho u phi is 0, so rho u phi is constant. Then the convective flow, of course, if we consider constant flow, we have rho u constant, then the variable phi will be transported in the domain, and it will depend on the direction of the flow. Okay. So we see that the behavior of pure diffusion and pure convection is very different. And when they are both here at the same time, when you have both convection and diffusion, we'll have a profile, and if we solve for the exact solution, we will have an exponential profile. So we'll try to develop numerical techniques together that will be able to accurately compute cases where you have both convection and diffusion. Let us start first by finding, if you want, the expressions. Okay, we want to solve for the conservation equations in the different control volumes to be able to determine the coefficients. Our purpose is to consider a certain control volume, write summation of fluxes here equals 0. Here you don't have a source term, so your equation is summation of fluxes equals 0. Summation of fluxes getting out minus summation of fluxes coming in equals to 0. And then you will replace, if you want, derivatives by delta d phi by dx by delta phi over delta x, and you will identify what are the coefficients of phi at p, phi at west, phi at east, etc. Here we'll take 1D case. We have already taken 2D case for case of pure conduction. Now, for the convection diffusion case, we'll take a simpler domain, 1D Cartesian domain, and we'll develop together the equations. So the idea will be, as usual, in a first step, to divide the domain into several cells. And for each cell, we will write the conservation equation. Let me take the cell centered at P. This cell is subjected to convective and conductive and diffusive fluxes. So I have through the west face, so you have west and east faces. Through these faces, you will have fluxes. And on east face, we have a conductive flux and a convective flux. The same for west and east faces, we have two types of fluxes, convective and conductive. So the idea will be to express these fluxes. Okay, let us start with the convective flux. We said that the expression of the conductive flux is the following one. So we have first, this is a convective flux at west face. And we know that the convective flux is expressed as, so here, if you, all you have to do, if you want, if you remember, in a convection flux هو rho v times the variable times the area. Okay, because here what you do is you integrate over your control volume. And as we did with diffusion, نفس الconcept. This is the flux. This is the expression of the flux of convection, rho v phi. I do dot product the surface of the face. Okay, and again, because you have if you want constant thickness لجوا, the thickness will cancel out. So when you multiply, or you can do the analysis per unit thickness, or you can say the thickness T, whatever is the thickness T, since no variation along the thickness, T will appear in all terms and it will cancel out at the end. So I can define then my surface vector here at west. My surface vector at west has a normal vector in the negative direction. And I have that the height is delta y, and the thickness T will be simplified. So I can write that S west is minus delta yi, and S east is plus delta yi, because for the east face, it's like this. Okay, and when I do rho v phi dot s, automatically for the outlet flux I will get a positive result, and for the inlet flux I will get a negative result, considering that the velocity is along the positive direction. Okay, so whenever you do rho v phi dot s, okay, you will get your flux, and it will be, if it's positive, this means it's a flux coming out of your domain, If it's negative, this means that the flux is coming inside. The same for diffusion, as we have seen in the previous chapter. So now, if I do the dot product for the east face, what do I get on the east face? On the east face, I get plus rho u phi times delta y at east. This is the convective flux getting out from the domain at east. Of course, this is for positive u. إذا u negative ساعتها شو بيصير؟ هيدي اليو إذا صارت negative بيصير الفلux in. So automatically بيقلب sign لأنه if u is in this direction, then the flux will come in of the control volume instead of getting out. So this expression is valid for any case. It's valid for u positive or negative. Okay. Now for the west face, you get, since SW is minus delta YI, you get minus rho u phi times delta y at west. So these are the expression of the convective fluxes. The diffusive fluxes, شفناهم already أنا وياكم in the previous chapter. We get minus diffusivity times d phi by dx delta y at east. وماينس minus يعني plus tau d phi by dx delta y at west. So these are the summation of fluxes coming out minus summation of fluxes coming in equals to 0. Now, the challenge is how to compute the values at faces. Yani I should use a profile. Okay, I should use a profile. If you remember in diffusion, for example, تنطلع الديفيوزيفيتي على الايست وعلى الويست. We did harmonic interpolation. This is if tau is not constant, of course. Okay. وتنجيب ال d phi by dx, we said that d phi by dx at east can be computed as phi p minus phi east minus phi p over delta x east. And to compute d phi by dx at west, we do phi p minus phi west over delta x west. Now for the convective flux, okay, for the convective flux we have a problem. How to compute the variable phi at east face? What is phi at east and what is phi at west? Can we use the same, can we use a linear interpolation and, for example, say that I can consider that phi at east face is phi p plus phi east over 2? Or it's better because it's convection and the direction of the flow is positive, is to say that the east face will be affected more by phi at p, more than phi at e. Yani maybe it's better to say that phi at east is equal to phi p because u is positive, and phi at west will be affected due to convection, will be affected by the value just before it. So phi west face equal to phi big W. So you have several approach. This one, which I illustrated for you here, is called the upwind scheme. This means that I consider the effect of flow direction on the value of the variable at the face. However, if I take phi east plus phi west, let's say to compute phi here, the value here, if I say let me take phi west plus phi p over 2, ساعتها I'm considering in convection the value of phi here is affected equally by variables at these 2 points. If we do a small analysis, the Hidakle scheme is more logical in convection, because in convection the direction of the flow is very important. And if I only have convection, أكيد هيدي الفيس will be affected by phi w and not by phi p. Because here I have both conduction and convection, يعني I can if you want I can compare the schemes. يعني I can try to do the upwind scheme and see the result, and I can try what we call it the central scheme, just one, and see the results. And now from our analysis we'll come with recommendations. ونحن هنعمل examples to understand which assumption is good, which scheme is good, and in which case. In which case it's good to take the upwind scheme, in which case it's better to take the central scheme. These are the questions that we will answer in this chapter. So now we'll start with the central scheme as we talked together. So what is the idea of the central scheme? The idea of the central scheme is to compute, for example, phi at east, is to take a linear interpolation between points P and E and say that phi at east can be computed as phi E plus phi P over 2. And for phi at west, also same procedure. I take a linear interpolation. I say that phi at west face is phi at point P plus phi at point W over 2. If we do this, we replace into our equation. So if we do this assumption, phi at east will be replaced in the equation we found, function of as phi big E plus phi big P over 2, and phi at west will be replaced by phi P plus phi W over 2. And now we have transformed then our equation from a differential equation to a numerical one, and we can calculate then what are the coefficients AP, AE, and AW. Okay, all we have to do is to take, if you want, كل الكويفيشنت اللي multiplying phi E بنجمعهم مع بعض. يعني if you look at this equation, for example, if you look at this equation, what do you have? Let us see what is the coefficient of phi east. You have first rho U delta Y at east. So delta Y, لأنه delta Y east to west هي zeta. You have here a rectangular component, a rectangular control volume. So rho U delta Y over 2. We have also for the multiplying phi east, we have also minus tau delta Y over delta X at east. So this is the coefficient, this is coefficient of phi east, this is AE. This is equal to AE, okay? We do the same for A west, to get A west. To get A west, we add all components of multiplying phi west. So for phi west, I have first minus rho U delta Y over 2, minus rho U delta Y over 2. And we have also this coefficient. So don't forget, here you have a minus outside, okay? So you have a minus outside and you have a minus here, so minus minus plus, and you have a minus here again, so minus. Minus tau delta Y over delta X west Okay, so this is A west. And finally, for AP, for AP, the coefficient of phi P, AP equals 2. So first you have phi P is multiplied by first rho U delta Y east. So you have AP is rho U delta Y east minus rho U delta Y west plus tau delta Y over delta X east plus tau delta Y over delta X west. So once you find the coefficients A east, A west, AP, then you can solve your equation You solve your system using different methods mentioned before. Now, let us see if the central scheme will work well or not. In problem of convection diffusion, pure convection diffusion, we know the expression of the analytical solution, and we will try to compare with it. We will see that the central scheme will operate well if the if the conductive term or if the diffusive term is dominant over the conductive term, okay, in general. And لأنه كل ما conduction is better, يعني is more dominant, بيصير نحن عم نقرب على ال pure diffusion problem, والcentral scheme will perform well. لأن نحن بنعرف إنه in pure conduction we have a linear profile. بينما كل ما زاد ال convective effect يعني ال central scheme ما بيعود very accurate. So as you will increase, we will see large differences between the actual solution and numerical solution. And we will see together this in examples to see better this effect. حتى we can show that if we increase the number of elements, this can enhance the prediction. Okay, so let us try to compare with the case of upwind scheme. If you want to use the upwind scheme, what will be the difference? So whenever we use the upwind scheme, as I told you, when you use the upwind scheme, you should take into consideration the direction of the flow. So if your flow is directed in the positive direction, then phi at, when you want to compute phi at east, you will take phi east equal phi p, and phi west face equal to phi w. However, if u is negative, so if your flow is in the other direction, you have that phi at east face will be equal to phi at point E, and phi at west face will be equal to phi at point B. So whenever we use the upwind scheme, we should know the direction of the flow to be able to determine the coefficients. Okay, so same technique as usual to get the coefficients. We write the conservation equation, okay? And then when we replace here, يعني مثلا here we should say, how is the velocity? Is it positive or negative? If the velocity is positive, we have expression of coefficients. If the velocity is negative, we have another expression of the coefficients. So let us take, for example, the negative case. If u is negative, then I will replace here phi east by phi at point E, and I will replace here phi west by phi at point P. For the diffusion term, the method is the same. I don't care for the direction of the flow. This is computed as delta phi over delta x. Okay, and now I can define my coefficients. For each scenario, if u is positive, I get my coefficients. If u is negative, I get another expression of coefficients. And I can test my solution for different values of velocity. And I can see that in general, when convection is dominant, the upwind scheme will perform better than the central scheme. And as I told you, we'll see this in example, in numerical examples, to see how the upwind scheme sometimes can perform better than the central scheme. And in other cases, the central scheme will be better. So it depends on the ratio of convection to diffusion. And we'll define together a dimensionless number called Pecklet number that will help us into knowing